so far we covered what, like 3 units. The first unit on errors, I wouldn't call it a unit, just kind of an introductory way of thinking about numerical methods. Then the first unit we covered in class was on solving algebraic equations, whether they are linear or nonlinear, right? We did linear solvers, systems of linear equations, etc. And then we did nonlinear equations, systems of nonlinear equations. Then we went on curve fitting. We did interpolation and regression. The last unit is going to be on ordinary differential equations. But there is one topic that's an orphan topic that I could not fit into any one of those units. And I'm going to try to finish it today because I think it's a useful tool in your arsenal as you do engineering. You could argue that we could fit this topic, which is numerical integration. We could fit it under data analysis, which arguably would be under interpolation and regression because that's sort of data analysis. Or you could fit it under ordinary differential equations, but not quite, because with ODEs, we're integrating the ODE, but we mean something different by integration. So we're just going to call it an orphan topic. The orphan unit in this course is going to be on numerical integration. And as usual, I'll start with a little example, maybe not very motivating, but an interesting example. This shows a plot. On the y-axis, you're looking at the metric tons of CO2 per capita worldwide for the entire year. Like in 1960, we emitted, 3.1 million tons of CO2 per capita in the entire world. And versus year, so at each year, there's one data point, 1960, 1961, 62, all the way to about 2015, I think. So these are the data of millions of metric tons, okay, emitted per year. Now, suppose you want to calculate the total amount of CO2 emissions throughout all of these data. So integrate the whole thing. What would you do? You would integrate it how? Yes. Well, like how? How would you do it?
You could add up all the points.
Okay. Ethan? No. So what would you do? Connor?
I'd find a model function for that, and it could be like even a spline, could be something like a giant polynomial, and then I would just integrate that algebraically.
Algebraically. Why? Because the spline or the polynomial, we can have an exact analytical solution for that. Okay. Ethan? Trapezoids? Yeah. Yes, that's what we're going to learn today. Abigail?
So it's like interpolation, like you interpolate between each point.
And then, so you do the interpolation is going to give you a formula for how the data looks like, right? Yeah. But then we want to integrate. We want to sum we want to find the area under this curve. An integration of those. Okay. So all of your answers are correct. Okay. So what Miles suggested is called the Riemann sum, which is identical to what we are going to call the left point rule or the right point rule. What Connor suggested is going to be what we call the Newton-Cotes formulas, where we're going to fit analytical functions between these points and then simple or easy to integrate functions like polynomials between these points, and then we're going to subsequently integrate those analytically. And what Ethan suggested, the trapezoidal rule, that's a special case of what Connor suggested, and it's fitting a straight line, and what Abigail said, putting a straight line between each 2 points and then calculating the area under that straight line between those 2 points. That gives you a trapezoid, right? Okay, so let's do it. Learning should be a fairly easy chapter, okay? At the end of this chapter, you should be able to define what quadrature and numerical integration means. They're the same thing. Okay, the word quadrature comes from an ancient mathematical look when they were calculating areas of land. That's how integration started. People were trading land and things like that. Or like, my land was the area of 10 cubits or something, or whatever units they used, right? Give me 10 horses for that. But they used to draw quadrilaterals on those pieces of land, right? And that's where the word quadrature comes from. It's drawing quadrilateral elements under the curve to do the integration. calculate the area under an analytical function using Newton-Cotes formulas, calculate the area under a discrete set of data points, sorry for the typo, data points, okay, using Newton-Cotes formula. So what we looked at, the example we looked at is discrete data, but also sometimes you're interested in integrating a function where you don't know the antiderivative to, right? So typically what you learned in calculus is you would find the integral between a and b of some function. You'd first get the antiderivative and you evaluate it at b minus its value at a, right? But some functions do not have an antiderivative, so, and they're very complex, so you have to do them numerically. Use the left point, right point, midpoint, trapezoidal, and Simpson's 1/3 and 3/8 rules to calculate the integral of a function. So those, you can do those analytically by hand. We're going to learn about all of those techniques. Determine which of the above integration formulas apply to equally spaced and unequally spaced data. So the data I showed you is equally spaced. There's one data point every year. But what if, you know, for a few years, they didn't measure the data, or like they measured every half year and then every 3 years and then every 2 years, right? If it's unequally spaced, some of the methods we're going to talk about are not going to apply to discrete data. And then finally, estimate the error bounds. And this is just like one slide just to show you the error bounds for the midpoint, trapezoidal, and Simpson's rules, okay? All right, so here's the abstraction of the problem, or the rational formulation that we're going to work with. We're drawing a curve, okay, this red curve, and you want to find the area under this curve between the 2 points A and B. If you are given the function f of x, the red curve, could be like sine squared x or whatever, right? This is expressed as the integral from a to b of f of x dx, right? So the one interpretation of the integral is this is the area under this curve, okay? We're going to look at analytical functions first. All right, Newton-Cotes integration. The idea of Newton-Cotes integration is to approximate f of x as a polynomial and then perform the integration on that polynomial analytically and then evaluate it. Why? Because the polynomial is easily integrated, right? The integral of x is x squared over 2, the integral of x cubed, right? So it's very easily integratable, right? So we're going to approximate that function with a polynomial or a series of polynomials stacked next to each other, and we're going to approximate that integral by integrating those polynomials, okay? That falls under the general category of what we call Newton-Cotes integration approach. The idea would be choose the order of the polynomial. This is going to determine the number of points that you need to determine the coefficients of a polynomial. So if you're choosing to approximate the function with a quadratic, right? You have a0 plus a1x plus a2x squared. You need 3 data points on that function, right? To be able to find a0, a1, and a2, and then you'll be able to do the integration. How do you pick those data points? We'll see. Integrate and then choose the points and find the coefficients of the polynomial, and finally integrate the polynomial exactly on the interval in question. All right, so the first polynomial we're going to look at is going to be a constant. Okay, that's a polynomial of order 0. So we're going to approximate the entire function as a constant on the interval a and b. All right, that might be very surprising, and you're right. For a function that varies a lot between a and b, this seems to be a very bad choice, but we will see how we can actually use this approach to build very accurate approximations to the integral. Let's see how this works. You're going to say that f of x is equal to a constant, is approximated by a constant, and then you substitute that constant into the integral, right? So the constant comes out, and then the integral of f of x is that constant times the integral of f of x between a and b is simply that constant times the width of that interval, b minus a times that constant, okay? We haven't chosen the constant yet, all right? We have not chosen the constant yet. There are a few ways to choose it. One of the ways to choose the constant is to say, well, you know, I'm going to approximate this entire function over the interval a and b by the value at a, f of a. So if you choose f of a as your constant, right, then you're approximating the area under the curve by that rectangle, right? F of A times B minus A. You approximated the entire red curve by that horizontal line, F of A, right? So you're committing an error, clearly, okay? Might not be the best choice, but it's a choice, okay? So that gives you the left point rule. The integral of f of x between a and b is b minus a times f of a, okay? And that's the left point rule because a is the left point, all right? Now, you know f, so you can evaluate f of a very easily, all right? So you can compute this. Another choice would be the right point rule, where we approximate the function by f of b. So if you do that, then you're approximating that entire function by that horizontal line at f of b, right? And you're approximating the integral by the area given by this square, right? So in this case, you're overestimating the area, right? Because there's this little spot up there, okay? And then the integral is f of b times b minus a, right? Pretty simple, you know, and not very accurate, you might say, but we'll see how accurate this can be. There's actually an infinite number of choices for this constant. You can choose that constant to be f of a plus b over 2, right? Or f of a plus b over 3. Any point on the curve can be chosen to represent that constant, all right? One popular choice is actually f of a plus b over 2 is the midpoint rule. So in that sense, you say, okay, I'm going to take the midpoint, a plus b over 2. I'm going to make the function, approximate the function by the value of the function at a plus b over 2. And that gives you this square, this rectangle. Now for this curve, this kind of tends to compensate for the error, right? It over predicts the area on this side and under predicts it on the other side. And in a way, it kind of always tends to adjust itself. It's a very accurate method, actually, this midpoint rule, okay? That's called the midpoint rule. But frankly, you can design any method you want. You can pick any point in this interval and use it to make the function constant and approximate it, okay? The challenge with the midpoint rule, though, is that you require the function value at the midpoint, okay? When you know the function f, that's not an issue because you can just evaluate f at that midpoint. But as we will see later, when you try to apply the midpoint rule for discrete data, if the data is not equally, first you have to skip every other point to get the midpoint between two data points. And if the data is not equally spaced, there is no way that you can apply the midpoint rule, all right? Okay, so let's first learn a Python routine to allow us to do integration so that we can compare these methods to what Python is going to give us. The standard method to integrate an analytical function in Python, or a continuous function, not discrete data, a continuous function in Python is from scipy.integrate.quad. So you import from scipy, you import integrate, and then you call integrate.quad, and it has the following minimum number of 3 arguments. The function name that you want to integrate, or the function routine, could be define my function of x, and that could be sine x squared times log x times e to whatever, right? Whatever function you have. So you pass it that routine, and you give it the interval a and b, and it will build a very accurate approximation for the integral of f of x between a and b. Okay, integrate.quad. So that's going to be our go-to gold standard, our go-to reference to check what our methods are doing, right? It's this idea of verification. Okay, we're not going to be working with analytical solutions, all right? We can work with analytical solutions, but in this case, I can hit 2 birds with 1 stone. We'll learn about quad, we'll learn about the new methods, and we can compare the two, okay? Okay, so these are the 3 methods we have. The left point rule, b minus a times f of a, approximation of the integral. The right point rule, b minus a times f of b. And b minus a times f of a plus b over 2 for the midpoint rule. Okay, so now we're going to do our first coding activity. We're going to develop 3 Python routines that implement the left point, right point, and midpoint formulas. The routines should allow you to pass an arbitrary function, okay, that you're gonna integrate between A and B. So we'll need at least 3 arguments for our routines: the function name and the interval A and B, okay? And then once we write these functions, we're gonna use them to calculate the integral between 0 and 1 of 1 plus 0.5 sine squared 1.75 pi x dx, and we'll compare with scipy dot quad, okay? Dot integrate dot quad. All right? Okay, let's do it. Get your Jupyter notebooks up and running. Okay. Can anyone see my keynote? Oh, there it is, hiding over there. Okay. All right, so go ahead and start your Jupyter notebooks. I'll start it right here in a minute. Okay. Start mine right here in a minute. Okay, we're gonna do, I'm gonna create a new notebook. All right, so let's call this numerical integration. Numerical integration, okay. And let's go ahead and import our boilerplate. Import numpy as np, and then I like to do matplotlib inline, and then config inline, oops, backend dot figure format equal scalable vector graphics, import matplotlib dot pyplot as plt, and then from scipy import integrate, okay? So this is our first activity. Let's call it activity 1, all right? We're gonna define the function f of x. First, we're gonna define the function f of x, 1 plus 0.5 sine squared 1.75 pi x. I wanna see what this function looks like, okay? So I'm gonna go ahead and define it, just see what it looks like, explore it a little bit, define my function, f of x. Let's see, can you guys see in the back? You see okay? No? Is this better? Sorry. Is this better? Okay. Yes, I have become, I worked on my vocabulary over the weekend, and I'm so much better now. Oh my gosh. In my native language, there's no difference between arm and hand. And my 2 kids, they keep correcting me because, like, we're talking, I'm just, you know, use your hand to open the door, use your arm to open the door. It's like, no, use my hand, Dad. I'm like, just go to your room. And use your hand to open the door. All right. Dot sign 1.75 times np dot pi times x squared.
Oh my God, there's a what?
No, dot pi. Oh yeah,
Just,
3.14.
how many digits does it go to?
To whatever floating precision you need, like by default 64 bits, I think. So probably 16, I would say 16 digits, but I don't know. All right, so let's plot this function. I'm going to create a linspace, np dot linspace from 0 to 1, and plt dot plot x, my f of x. Okay. All right. Oh, look, that's the function. Okay. Here's a little trick also. And I'm not going to explain how, but there's like a lot of Googling. If you grab a handle to your plot, you can use a function called axis. It's like a standard nomenclature they use to grab the handle for this plot. Check this out. So I'm going to fill the area between my f of x and x, okay? Edge color equal, let's say, black. And then face color. You don't have to do this. I'm just doing this. Let's say light gray. Okay, let me see. My f of x. Okay, look at that. Okay? So I filled the area between x, between the x-axis, x, and f of x. And you can do this to do all sorts of fun stuff in Matplotlib. Okay? All right. Let's go back to what we need to do here. We need to define now 3 routines, one for the left point rule, one for the right point rule, and one for the midpoint rule. So let's call them def left rule. And the left rule is going to take an arbitrary function f and an interval a and b. Oops. And it's going to return f of a times b minus a. That's it. And then def right rule, also f a b. That's going to return f of b, that's the right rule, right, times b minus a. And finally, midpoint rule, also f, a, and b. Then return f of a plus b times 0.5, a plus b over 2 times b minus a. Okay? Those are the 3 definitions. Let me add a few cells here so you can see. Okay, a little bit. Okay, right? Those are the 3 definitions up there. F of a times b minus a, f of b times b minus a, and f of a plus b over 2 times b minus a. Okay? So now we can evaluate the integral of our function. We can call left rule. Oh, I didn't evaluate this. Okay, so let's evaluate this. Then I'm going to call left rule for my function f, and I'm going to give it the interval 0 to 1, and it's going to return 1.0. Right rule, my f, 0 and 1, and it's going to return 1.25. Okay. And then midpoint rule, my f, 0 to 1, and it's going to return 1.073, some number. Okay. Now we know this is not going to be very accurate at all. So let's compare it with quad, the standard method from SciPy.
Can you go back up to your function? I think I just did wrong.
Okay.
Oh, plus.
1 plus 0.5 sine whatever squared.
Also, for some reason, the x.fill, it's saying that x.
Yeah, don't do that. Yeah, you want. Okay, so let's see what quad is going to give us. If you go integrate, okay, let me add a few cells at the bottom here. Okay, integrate dot quad. Okay, see the function signature. You need at least 3 arguments: function, name, a, and b. Okay, now if your function takes more arguments, you can pass them here. Like if it has a bunch of parameters, okay, you can pass them in that 4th option here, like we did with nonlinear solvers, etc. But we're not doing that here. So my f, 0 and 1. And look at that. Now, integrate.quad was actually closer to the right point rule than it is to any of the other rules. Okay, we're still like kind of in the darkness here. Like, what are we doing? This is like very inaccurate. We'll see. We're going to build on this and to make way more accurate functions. Okay. Integrate.quad is very accurate, and it estimates the error. So it gives you an answer for the integral and estimates the error at 10 to the minus 12. So it's a very accurate method. Okay. Okay. Cool. Yeah. All right. So the first one is the value of the integral. The second one is the error committed in this integral. It's an estimate of the error, okay? All right. So now we can go back to the slides and let's see what we can do next with this. All right. Okay. So how do we increase the accuracy of these methods? Clearly if you look at that function that we integrated, it varied a lot between 0 and 1. And who knows what was going on? The midpoint rule was there was some cancellation in the area or some overestimation or underestimation. Clearly applying the left point, right point, or midpoint rule, a common sense would say like, yeah, you can't apply it for the entire interval, right? It's especially if the interval is large enough and the function varies a lot in that interval. What if we can take that big interval where the function varies a lot and subdivide it into an arbitrary number of smaller intervals, right? We can do that because we know the function, we know the interval a and b. Let's say we split it into 50 subintervals or 100 subintervals, and then go in each subinterval, we apply those same methods, either the left point, the right point, or the midpoint. Wouldn't that commonsensically, right, give us a little bit better approximation? Yeah, absolutely, right? Because now we're applying that approximation where the function is a constant to a smaller interval where indeed, if the interval is small enough, the function doesn't vary much along that interval. So approximated as a constant in that very small interval is a good approximation, okay? So that's what we're going to do next. So the procedure of dividing the area under the curve into smaller areas is called quadrature. Numerical integration, and then for here onwards, we kind of call numerical integration or quadrature. We're going to use the same word for those two. But also when you take a big interval and subdivide it into many subintervals, that's called a composite rule. So when you apply when I ask you to apply the composite left-hand rule to an integration, what I mean by that is you're going to take that interval and subdivide it into subinterval, okay, and then apply the left-hand rule to each subinterval and add up all of the intervals together. Composite rule. Composite left hand, composite right hand, composite midpoint. We're going to see composite Simpsons, composite trapezoidal rule. Okay. So that's kind of how it works. I'm showing here so you take the interval, you split it into however many subintervals or segments you want, and then you apply midpoint, left point, or right point rule to each one of those subintervals. You get the area and you add them up together. All right? So that's going to be our next coding activity. We're going to develop a Python code that implements the composite left-hand rule, right-hand rule, and midpoint rule, okay, for an arbitrary function and with an arbitrary number of intervals. So we're going to create these routines. The arguments for those routines are going to be the function name, the interval a and b, and then the number of segments. Okay? Think about the Taylor series. When we did the Taylor series, we were able to choose how many terms we wanted in that Taylor series. Here we're going to choose how many segments we want to carry out that integration. Okay? Now here's some hints. What we're going to do inside that routine, the composite left-hand rule or the composite right-hand rule, we're going to take that interval, create a linear space on that interval of equally spaced points, right, which will help us define the equally spaced subintervals or segments, and we'll apply the left-hand, right-hand, or midpoint rule to each one of those segments. All right? Let's go ahead and do this in Python. Okay. So we'll call the first one. Once we do the first one, the others will be very easy to just copy and paste and changing the point. Okay. Zoom in a little bit more for those in the back. We're going to do define composite left rule. Okay. That's going to take a function f, the interval a and b, and a number of segments n. Okay? So you can choose whether n means the number of points or number of segments. It really doesn't matter because you end up with one more segment or another. It's not a big deal. Okay? Here we're going to refer to n as the number of segments. Okay? All right. So first we're going to create a linspace. Create a linspace to define n segments on AB, right? We're going to do this by creating x equal numpy.linspace from A to B. Now, linspace creates a number of points. So for n segments, we need n plus 1 points, right? Because with like 3 points, you have 2 segments, 4 points, you have 3 segments, and so on. So if n means it refers to the number of segments, then length space needs to be n plus 1 points, okay? Then our integration result, we're going to create a variable that is 0. And then for each interval, we're going to add the area, okay, in that variable, to that variable, as we build up the total area under the curve. So we start by result, go 0.0, right? And now we're going to loop over all of those points, okay, on the length space, right? And then do the integration over each interval. So here's how I like to do it. For I in range 1 to n, okay, then A is xi, and B is xi plus 1. Oops. So actually, we can go from 0. We should go from 0 to n, right? Okay. So once you enter the loop, you're indexing with I. Then we're going to grab the first x value and then the one next to it. That defines a segment, right? This is the left point of the segment, and this is the right point on the segment, right? So A and B. So that's one of the mini segments. Agreed? So in other words, now you just simply say result. We're just going to do the integral. We're going to implement the left rule now on this AB. Okay? On this AB. So we're going to do B minus A times f of A. This gives us the area on this mini segment, and then we add it to our result. Okay? And once we're done, go back, return result. Okay, so let's see how this does. Remember, the exact answer, or the truth, is 1.272, right? So let's see. Composite left rule for my f, 0 to 1. Let's say you want to put 50 points. Look at that. Previously, the left rule gave us 1.0, right? Then with 50 subintervals, it gave us 1.27, pretty close to to the true answer. Let's do 100 points. It's going to get even better and better, right? With more and more points, look at that, starts getting closer and closer to that answer, right? Right? Because then that silly idea of approximating the function as a constant over the entire interval doesn't make sense. Of course it doesn't make sense over the entire interval, but when you apply it to a small interval, it makes total sense. Because if the interval is small enough, the function probably varies very little, and therefore approximating as a constant makes total sense. Okay? Yes? No, integrate.qu is a little bit more complicated than that. It does like some some advanced stuff. So instead of using equally spaced points, it chooses a less number of points and chooses them optimally. There's some theories over there where you optimally choose those points to give you the most accurate answer. So it's a little bit beyond what we need to learn here, but the concept is kind of the same, okay? So here we're just choosing the left point, but there are techniques to choose a more ideal point in between in that interval. All right, so now do the same for the right point rule and for the midpoint rule. Choose one of them, do it, and then run that integral. So the only thing that's going to change for midpoint or right point rule is this one, right? For the right point rule, this is going to be f of b. For the midpoint rule, this is going to be f of a plus b over 2. So create other routines, composite right rule and composite midpoint rule, okay? You can just copy and paste. Composite right rule, f of b. And then composite midpoint rule, f of 0.5 times a plus b. So I'm going to try them out. Composite, midpoint rule, my f, 0, 1, say 50 points. Pretty accurate. Actually, the midpoint rule is one of the very accurate methods that we're going to see. With 50 points, we're able to get even closer to quad, which is a very accurate method. Okay. With the right point rule, composite, for some reason, the right point rule is not showing up. Okay. Composite, there you go. Right rule, my f, 0, 1, say 50 points. Again, all within the same ballpark, but they're much closer to the truth. Okay? Composite rules is the way to go, right? You have a big function, you split it into many small intervals, and then you integrate, you calculate the area in those smaller intervals, all right? Do you need some more time with the code? It is the more accurate method out of those two, okay? Because it tends to balance. If you're overcompensating on one side, you're going to undercompensate on the other if your curve is going up or going down, right? So you tend to cancel those errors.
And this is all done with evenly spaced data right now?
Not evenly spaced data. This is a continuous function. You can evenly space it or not. It's up to you. So instead of lint space, you could create a log space, for example. Then the data wouldn't be evenly spaced. This will still work. Okay? It will still, because you have the function, you can evaluate it anywhere you want. With discrete data, it becomes an issue. We can't use the midpoint rule with discrete data unless it's equally spaced. So we'll see that. Okay? Let's go back to the slides. All right. All right, what about discrete data? Okay. So if you have some discrete data, and notice the data here, is just equally or unequally spaced, it's just shown as discrete data. Then the left point rule applies readily because you can take every pair of points and take the point on the left, right? And then evaluate the area. Right? So between x1 and x2, you take f at x1 and multiply it by x2 minus x1, and then same thing here. Whether the data is equally spaced or not, it doesn't matter, right? Because it's just using one edge of the interval. The right point rule also applies readily, because all you need to do is go through data pairs. Whether those data are equally spaced or not doesn't matter. You just have to pick either the left point or the right point. Okay. Now, what about the midpoint rule? Kind of gave you the answer. It does not apply to discrete data unless the data is equally spaced. And if the data is equally spaced, you have to skip every other data point to get the midpoint. Right? So in a way, you're losing your resolution just to pick the midpoint. You have, 100 data points, so you're really doing 50 intervals, right? But then you have to also skip every other point, which could be a programming nightmare. But if the data is unequally spaced, you cannot apply the midpoint rule because you do not have the value of the function at the midpoint, right? If it's not equally spaced, by definition, you don't have the data at the midpoint, all right? So, with unequally spaced data, you got to go to either left hand or left point or right point rule, okay? In general. We're going to learn a more accurate method shortly for discrete data, whether equally spaced or unequally spaced. All right. But first, for discrete data, the equivalent of quad, or one of the versions that we use, so quad cannot deal with discrete data. Quad only takes a continuous function. You have to pass a continuous function to quad, right, like we did. You cannot give it discrete data xi, yi. If you have a discrete data like the CO2 data that we have, and you want to integrate those, one routine that is quite accurate comes from NumPy, and it's called TRAPZ. You probably saw that in MATLAB. You probably remember it from MATLAB. It stands for the trapezoidal rule, We're going to learn how to do the trapezoidal rule too. But we're going to use that as our gold standard now as we explore left point and right point rule for discrete data. Okay? All right, so now here's the question. Using the left point and right point rules, develop a Python code that integrates any discrete data. Right? So the left point rule, right point rule can integrate any discrete data. So your routine just needs to take xi and yi, right? And then apply it to calculate the total world emissions of CO2 per capita, and then compare your results to the TRAP-Z routine from NumPy. Now, I didn't mention this, but the TRAP-Z routine at a minimum takes 2 arguments, the y data and the x data. Okay? Y is the dependent data, and xi data is the independent variable, and just returns an integral for you. So we're going to implement our own left point and right point rules for discrete data, okay? And then we're going to compare with numpy.trapz for the CO2 data. Okay. Where do we get the CO2 data? You can download from co2worldemissions.txt from the Canvas integration module. Okay, you should have that text file on Canvas. Drink some water. So far we only dealt with continuous functions, okay, where we could evaluate the function at any point. Next, we're going to do this with discrete data, where you are just given some data. You can't evaluate it at any point you want. You can say, oh, I'm going to approximate it or interpolate. You are not creating any new information by interpolating, okay? So you might as well just stick with your discrete data. Yes, Brandon?
Oh, never mind. Where's the integration module?
In the Canvas. On Canvas, is there modules, under modules? Did I call something else up there? Quadrature, sorry. Quadrature module. Not integration. Thanks, Brandon. Let's fix this. Canvas, quadrature module. Okay? Okay. So let's go ahead and do this. So once you have the data imported, once you have the data downloaded, we're just going to load it up into we're just going to load up the data using numpy.load.txt. So let's see how this works. It's numpy.load. I know I haven't taught you about load.txt. I'm not going to teach you about it. Just do this now. This loads up a text file with the x and y data. This is just one way to access the data. There's a lot of these data, so we're not going to type it up. We're just going to load it up from a text file. If your data file is next to your Jupyter notebook, then you can simply start typing the name of the file and press tab. It will autocomplete. Okay? Now these data are delimited by a space, so I'm going to specify the delimiter and put space over here. Okay? Now this has a lot of data in it. The ones that I'm interested in are the year, which is in data, in the first column of the data, and the YI data, the CO2 emissions, is in the next column. Then what do we do when we have data? We plot it. And we're going to do a scatter. Okay? I'm going to do a grid in this case. You got it? This is the most naive way to load up a text file into Python. Okay? There are more advanced ways with pandas and CSVs, but this should suffice for what we need to do here. Okay? We all have the plot?
Like it's saying my file is wrong, but that's the name of it.
No, it's the CO2 world emissions.txt. Right?
Oh, different. Oh, different.
Yeah. Yeah, the world emissions. Yeah. It's capital CO2. Capital CO. Sorry, I keep scaring you every time. A capital O2. Oh my God, I'm coming here. Okay, do you have the file sitting next to the notebook?
Yeah, it's in here. I just right there.
No, you need the CO2 world emissions.txt. Yeah.
Sorry, I heard you say quadrature, and so then I was like, oh,
Yeah, this one.
should
This
be.
one. It's in the quadrature module. All right. All right, so we just give you another 17 seconds. Guys still having trouble? Oh. Grid. It's in Canvas under quadrature, a module. So if you go to modules, and scroll down to quadrature. What is it? Scroll up. Yeah, whatever. Numerical integration.
This
Yeah,
one right
yeah, yeah. Okay, so the module is actually called numerical integration, not quadrature. The file, the Python notebook is called quadrature, but that's not the file I want. I want CO2 world emissions.txt. So I'm going to go back here to the Canvas integration module. So I was right the first time. Okay. So all right. So we got the data now. We're going to implement a discrete version of the left point rule and the right point rule. All right. So it all starts with defining the subroutine. So discrete, let's say we're going to call it discrete left rule. Okay, and I'm going to give it xi and yi data. Okay. Now I'm going to store the area in some variable, call it result. We'll initialize it with 0 because we're going to keep adding to it. Okay, so that's why we initialize it with 0. And then we're going to loop over those data points, xi and yi. So first I need the length of those data points. And then I'm going to do a for loop because I need a counter so that I can do xi and xi plus 1. Okay? So that's why I do a range for I in range 0 to n minus 1. Then now I'm entering the data. I can access the data. Start by xi, and b is xi plus 1, right? And then f of a is simply y at I, right? So that's the left point. So now we're looping over the points, point at index 0, the first point, second point, third point, and so on. The difference between point I and point I plus 1 is going to give us b minus a. F of a is going to be the value of y at the left point, which is index I. Yes?
So why are we doing n minus 1 now? Okay, n plus 1.
So the other one was, so hold on. I think, yeah, this needs to go to n, actually. That should go to n. Right, because the range is open at the end, okay, and we're going to have, so, no, actually, hold on. It needs to be to n minus 1. Okay, because you're open and then you're going to go to, and the indexing, remember, this does, here's how to think about it. This is going to go from 0 to n minus 2, but at n minus 2, we're going to access n minus 2 plus 1, which is going to be n minus 1, which is the last index in the array. Okay? Okay. Again, I was right. Connor. That's right. Thanks, Connor. Okay. Now Connor is right this time. This needs to be xi, yi. Okay. Okay, how about we call them x and y? Okay, just call them x and y.
Now you're right.
Nobody's right this time. Okay, FA is yi, and then result, we're going to augment result by the area of this interval, b minus a times f of a. Note how I'm using nomenclature that is conducive to understanding the formula, right? The formula is f of a times b minus a. So I call this point fa just to reinforce that fact. If someone is reading my code, they'll be like, oh, he's doing f of a times b minus a. This is like the left point rule, right? Okay. Otherwise, I would have had xi plus 1 minus xi times yi and be like, you know, takes a minute to process. So sometimes clarity over efficiency is more important, okay? So let's do this, okay? Discrete. First, let's do trapezoidal rule. NP dot trap. That's right. I need to return. Now, Emily is correct. Return result. Okay. Trap Z. Okay, we're going to give it. So with trapezoidal rule, you give it the y data first, okay? And then you give it the x data. So the first argument is the y data, okay? So the total world emissions over these whatever 15 these from 1960 to 2015 is 232 million metric tons of CO2, okay? Per capita. Yeah. Okay. Yeah. So if you were born in 1960 and you've lived today, you've emitted 232 million tons. There's a yeah. No, the y-axis was millions. Per year, yep. Okay, so now discrete left rule, xi, yi. Oh, look at that. It gave us a pretty good agreement, okay, with the left rule, yeah. That's what NumPy wants, right? So trapezoid, if you look at the function signature for trap Z in NumPy, they want y and then x. Because x is optional in their view, because you might not necessarily have x data, so they space it by a unit, 1, okay? So in their eyes, x is optional. McKenna? Len x.
Well, that's not the MP.
Okay.
This is the thing.
MP dot trap Z. Scroll up.
Sure. I mean, theirs is probably more right than mine, but
Yeah, that should be fine here. Okay.
I mean, my graph looks like yours.
All right. Restart your kernel. You have the same answer. Probably have different. Maybe I need to update my NumPy. Yes.
I don't know what's up, but mine's like
You
off
got-
by like 1.
Yeah, you got a different answer. I actually have a. Okay, here's the thing. I might have a different data set than you do. I might have an updated data set. Okay, so probably I have more data than you do. So what is your last data point? So xi. My last data point is 2016. Your last data point is probably. Yeah. 2014? Yep. Okay. So I have a different data set. I have more emissions, yes. Between the,
Yeah.
yeah. Oh,
It looks right.
the discrete left rule,
Oh. This is supposed to be
Result.
I, not 1.
yes.
Yeah, I mean,
Yes. Okay. Good catch, love. All right. So now we can do the right rule as well. Okay, so we discovered that my data is a little bit off compared to your data. So I have 2 more data points. So it's okay if you get 223 as your answer. That's correct. Okay. I can actually, let me do this. 2 minus 2. Let me do this, 2 minus 2. All right. So now we're consistent, OK? And then if you do the right rule, it's the same thing. Right rule, except in this case, we want a yi plus 1 and f of b, and then discrete, right rule, and then we have xi and yi, gives you some number, all right? We claim this is an approximation to the integral. All right, let's continue. More accurate methods, supposedly more accurate methods. We're not going to talk about errors, etc., except in the last slide, I'm just going to show you some error bounds. The discussion on errors with integrals is a little bit, it's quite involved, okay? But you've seen kind of so far, you have a sense that the midpoint rule is somewhat more accurate, at least for a continuous function. Unfortunately, we can't use it for discrete data, but there is a function, there is a method that is as accurate as the midpoint for discrete data, and that's the method that you learned in Calc 1, which is the trapezoidal rule. The trapezoidal rule, now so far we approximated the function with a polynomial of order 0, that's a constant. What happens if we approximate it with a polynomial of order 1, which is a straight line? That's the idea. You take the function. For a straight line, you need 2 points. What better 2 points than A and B? You draw a straight line, and you evaluate the area under a straight line. That is your trapezoidal rule. You can literally derive it analytically. You can do the geometric, calculate the area geometrically, but you can also solve for this straight line and calculate the area under the line. You'll get exactly what we call the trapezoidal rule, which is what I understand you learned in Calc 1.
Do we need to solve for the line to solve the trapezoid?
Well, as you're building the method, yeah, you solve for the line, and then you integrate that line, and you get that formula. Once, you do it once, and that's it, right? And it's been done, okay? Or you can do it visually, right, by calculating the area of the trapezoid. Yes? Yeah, you can do that visually, okay? But this is the formula for the trapezoidal rule. F of A plus f of B times B minus A over 2. Now, what is so cool about this function is that, first, it is as accurate as the midpoint rule, which we know was a little bit more accurate with the discrete data. And what's great about it is that you can also apply it for discrete data, because you don't need any information at the midpoint. You only need the information at the left and the right points of that interval. So whether discrete data is equally spaced, unequally spaced, you can easily apply the trapezoidal rule. That's what numpy.trapz is doing. It's implementing this formula over every pair of data points. You can do the composite trapezoidal rule, which is our standard approach to get very accurate approximations of continuous functions. So you take, just like we did with the composite left rule, composite midpoint rule, you divide the interval into a series of segments, and you apply the trapezoidal rule at each one of those segments, okay? Okay, so now consider the function 2x plus 3, okay? I have this question for you. Calculate the true error in integrating y equal 2x plus 3 on the interval 0 and 2 using the trapezoidal rule.
Wait, wouldn't there be 0 error? Oh, did I just keep it away?
Keep it yourself, Miles. Okay, so we have one answer here. So in a way, calculate without calculating. We have another answer, which is the same. Okay. So calculate without evaluating the trapezoidal rule. What is the true error in integrating y equal 2x plus 3 on the interval 0 and 2? Okay, so Miles and Lev, Connor saying 0. 0, okay. And what was your explanation?
Because effectively what it's doing already is it's taking the 2 points and creating a straight line between it, and it's already linear as
Yes, okay. Thank you. So the error is going to be 0. So the trapezoidal rule, what is it doing? It's putting a straight line to approximate the function. If the function is a straight line, it's going to get that exactly. So there's absolutely no error committed in using the trapezoidal rule to integrate a straight line. Okay? Right? So that's where an understanding of what the method is doing will help you in making assessments like this. Okay? The error is 0 because the trapezoidal rule is exact for a straight line. Okay. Now, what is the true error in integrating y equal a constant on the interval a, b using the trapezoidal rule? Okay, we've got zeros, zeros. Okay. So you have a constant. You want to use the trapezoid, you want to put a straight line on that constant, the trapezoidal rule. You got to get that exactly, right? Because a constant is a special case of a straight line. It's a straight line with 0 slope. So the trapezoidal rule is going to approximate that function exactly. It's not going to approximate it. It's just going to get it exactly. Then you integrate it. The integration of the trapezoidal rule is an exact integration of that straight line. So the error is 0. Okay? All right. Now there's an even better approximation. Now what if we go to a quadratic polynomial, a second-degree polynomial? If you approximate the function as a quadratic on the interval a and b, then you get what's called Simpson's one-third rule. Now the challenge here is, how do you pick for a quadratic? Remember when we were doing interpolation, the quadratic has 3 coefficients, a0, a1, and a2. Right? So a0 plus a1x plus a2x squared. So you need 3 points, exactly 3 points, to find a0, a1, and a2. We already have a and b. It gives us 2 points. Where do we pick the third point? We pick it in the middle. In the absence of any other information, that's the best guess you could do. And then you fit a quadratic. You literally say, okay, I have a and f of a plus b over 2, f of a plus b over 2, b, and f of a plus and f of b, just like we did with interpolation, and you fit a quadratic. You solve for it, you integrate it analytically. That gives you Simpson's one-third rule, and this is it. Now, what is delta x? It's the spacing between a plus b over 2, and b. Okay, so let me... it's the spacing between, it's the spacing between those points, okay? So it's b minus a over 2. That's the segment. F of a is f of a, f of b is f of b, and f of a plus b over 2 is this guy. But it requires 3 equally spaced points on the interval a and b. This is a very useful formula. When, again, you're on an airplane, you want to calculate the area of some function, and you only have like a pen and paper, a problem that is common to everyone when they're flying, right? So you use Simpson's one-third rule, okay? Now, what is the error in integrating y equal alpha x squared plus beta x plus gamma on the interval a, b using Simpson's one-third rule? Okay. We got a 0. It's like I'm giving the answer away now with these questions. I should probably not ask them, because now when you see this on the exam, we're like, he's probably definitely means 0. Maybe I'll give one with an error of 1, exactly 1. It is 0, right? Because what is Simpson's one-third rule doing? It's approximating the function as a quadratic. If the function is a quadratic in the first place, you're going to get that exactly. If the data is quadratic anyway, then approximating the quadratic with a quadratic is that same quadratic. So then you integrate it, it's exact. It's going to give you the exact answer, okay?
If it's linear, does it give us it so?
So now Miles is saying, if you apply Simpson's one-third rule to a straight line, well, don't you think about that and solve it for the exam, okay? Okay. Simpson's 3/8 rule. Okay, now we're like on a roll. Okay, we're going to do now a cubic. Okay? So doing a cubic, you need 4 points, right? Because you have a naught, a1x plus a2x squared plus a3x cubed, correct? So you have a naught, a1, a2, and a3 to fit, to do the interpolation. So you pick 4 points. You have a and b. What do you do with the other 2 points? You also pick them equally spaced. So now the spacing is b minus a over 1, 2, 3, right? So you have 3 segments, right? And this is the formula for Simpson's 1/3 rule. 3 over 8 delta x. Delta x is the distance between any of these 2 points, b minus a over 3. And then you have f at a, which is x naught, plus f at x1, which is x naught, plus delta x, f at x2, which is x naught, plus 2 delta x, and f at b, which is that last point, okay?
So I just have a question. So why do we write that as 3 delta x over 8 instead of writing 3 times the b minus a over 3 over 8? Why don't we just put the substitute b minus a over 3 into the delta x?
Because the delta x, that has a special meaning when we are applying the composite Simpson's 3/8 rule. You express your error in terms of your interval spacing. So I need to have that interval spacing explicitly showing up in my answer, so that what happens if I cut my spacing in half or by 4, right? So what happens to the error? So then I can do a study just by changing that delta x interval, okay? It's just a matter of convenience. Connor had a question.
And so does this rule require that the midpoint between A and B be, like, it then be symmetrical on each side?
It doesn't have to be symmetrical. This just happens to look symmetrical here. But as long as you have f of x, you can evaluate it. You evaluate the function at any point in between. And we just happen to pick those points to be equally spaced because that's the easiest choice. There are other ways to choose those points, like Gaussian points or Legendre points. Right? You could be way left or way right. Yeah.
The error is 0.
Pardon me?
So even like if we go way to the extremes of the function, the error will still be 0 when we apply Simpson's 3/8 rule on a cubic.
On a cubic, it doesn't matter. Yeah, because on a cubic, the data is already, you're going to fit it exactly. Yeah, you'll fit it exactly. Yes. Okay, that's going to be the next question. Yeah, what do you think? Okay, so Abigail asked a great question, which is literally on the 2 slides down the road. And she asked if this applies to discrete data. Yeah. Yeah, you have, because if your data is not exactly at those points, if it's not equally spaced. Now, these are equally spaced. So if they're equally spaced, you have to skip every 4 points, right, to apply it. But if they're not equally spaced, you cannot apply it, okay? Okay, so now what is the error in integrating? Okay, this has become a pattern. So what's the error integrating a cubic using Simpson's 3/8 rule? It's exactly 0. Because a cubic is because Simpson's 3/8 rule approximates a function as a cubic. If the function is a cubic in the first place, you're going to get that exactly, okay? And then that formula becomes exact for a cubic, okay? And then Mars is going to ask, does it become exact for a quadratic, a straight line, or a constant? That's for you to figure out on the exam, okay? There you go. I gave you like 4 exam questions already to think about. Okay. So this is a summary of those formulas, all right? These will be on the final exam, okay? And I'll give you those formulas on the final exam, all right? Okay, give you those formulas on the final exam. Okay. So hold on, let me check what I have here on the slides. So I have a few examples here. All right, let's do some examples. So I have a few examples. I'm not going to go through them. But they're just essentially integration by hand. The midpoint rule, say you're trying to approximate e to the minus x. This was from one of the exams in 2019 or 2018. Integrate from 0 to 2 of the integral from 0 to 2 of e to the minus x squared dx. Excuse me. Using the midpoint rule, that's b minus a times f of a plus b over 2. So that's e to the minus, then 2 plus 0 over 2, and then you get a value, right? And then using the trapezoidal rule, You draw a straight line between the endpoints. Trapezoidal rule is b minus a over 2. So that's 2 minus 0 over 2 times f of a, or f of a, e to the 0 plus f of b. Okay, e to the minus 2 squared, right? Because you have e to the minus x squared. And then you get 0.882, whatever. Simpson's 1/3 rule. First, you need to get those points. Okay, so you calculate delta x, which is given by b minus a over 2. Okay, and then you have your points, f of a and f of a plus b over 2 and f of b. And then you just simply implement that formula. You can do it on the calculator. You get an approximation. And then the last slide, which is the most tedious by hand when you're doing the calculation by hand, is for the 3/8 rule. The hardest part is, the most tedious part is first you got to figure out those points. So first point is a, second point is a plus delta x, a plus 2 delta x for the third point, and the last point is b, and then you evaluate the function at those points, okay? Now we can do the same thing for all of these rules, the trapezoidal rule, the Simpson's 1/8 and 3/8 rules. We can apply them in a composite fashion, right? You take a continuous function, split it into subintervals, and then apply each one of those rules to each subinterval, okay? Same thing, you just implement those formulas exactly, okay? Now the question that your colleague asked, which of these methods is the easiest to apply to discrete data? Trapezoidal rule or Simpson's 1/3 or Simpson's 3/8? What'd you say? Trapezoidal. Why?
Because it doesn't require midpoints.
Yeah. Yeah, so for discrete data, the trapezoidal rule is the easiest because all you need are the endpoints for every pair of points. You don't need any information in between. Okay, you don't have to skip points if they're equally spaced and go into that mess. If the data is unequally spaced, forget it. Okay? Trapezoidal rule is the standard discrete integration method. Okay? Just like the midpoint rule is this kind of one of the standard exact continuous integration methods. Okay? Finally, I have a coding activity to implement the trapezoidal rule. Okay, now the trapezoidal rule, you can apply it to an exact function or a discrete data. It's the same, okay? Develop a Python routine that computes the integral of any function using the trapezoidal rule for an arbitrary number of segments, etc., and use it to calculate that function, and then compare it to quad. Oops. Sorry about that. All right, so we got like 4 minutes. Let's try to get this wrapped up. So we're going to do composite. So def, composite, trap, rule is function A, and B. I'm going to go ahead and copy paste one of the composite rules here. Everything stays the same except for the formula. So with the trapezoidal rule, we had b minus a over 2 times f of a plus f of b. Okay? So that's going to be 0.5 times b minus a, so that's b minus a over 2, times f of a times f of a plus f of b. Sorry, f of a, gosh, plus f of b. And then you can composite trapezoidal rule. You can apply it to our function f on the interval 0, 1, and it gives you an error. What is n? Oh. For I in range, hold on. Oh, yeah, we need a number of segments. My bad, my fault. Yes, you do, because we're doing the composite trapezoidal rule, right? So we're okay. So and then composite trapezoidal rule, 50 points, gives you 1.2726 whatever, right? So remember scipy.integrate, or integrate from scipy, integrate.quad, We had my function f on 0 and 1. That was 1.272. So it's pretty accurate. It's actually as accurate as the midpoint rule, actually a little less accurate than the midpoint rule. Okay? And we'll see, you'll see that statement in a minute. Okay, now we're going to do the trapezoidal rule for the discrete data. So we were stuck with the left point rule and the right point rule for discrete data. Now we have the trapezoidal rule, which apparently is quite accurate compared to the, almost compared to the midpoint rule, which we couldn't apply for discrete data. So we have now another alternative that's as accurate as the midpoint rule that we can use for discrete data. Okay? So we can go ahead and do that. And what I'm going to do is just copy the discrete right rule. And just do discrete trapezoidal rule. And all I have to do here is I need f of a2, so yi. Okay, and the result is b minus a over 2 times f of a plus f of b. And that's it. And then if we call the discrete trapezoidal rule on xi, yi, that's the CO2 emissions, we get 223.066. All right, let's see numpy.trapz with yi and xi. Look at that. It's actually exactly the same, okay? 255.499, right? Because numpy is implementing the trapezoidal rule. It's not a mystery. So some person decided, well, I'm going to put a trapezoidal rule in numpy. That could have been one of you, okay? Maybe one of you gets inspired here, develops their own integration method, and you can submit it to NumPy, and and you get it into NumPy. It becomes, we'll all end up using it. Okay. All right, we are done, and thankfully I have one more slide left, which is this slide. Okay, which is this slide. It shows you the error bounds on those methods. Midpoint, trapezoidal, and Simpson's 1/3 rule. Okay, b minus a is the full interval that you're dealing with. N is the number of segments that you're having. Okay, so you see that, and k is some constant. Okay, you see that the midpoint and trapezoidal rule, they share almost a similar error, except that the midpoint rule is a little smaller error. It's divided by 24. It's half the error of the trapezoidal rule. Okay, but they are about the same. There's 1 over n squared, 1 over n squared. When you go to Simpson's 1/3 rule, you have 1 over n to the 4th. Okay,